Question 2. A question about energetics. Write an equation including state symbols for the reaction with an enthalpy change equal to the entropy of formation of iron 3 oxide. So first of all, you've got to work out what iron 3 oxide is. Iron 3, Fe, is iron 3, means it's Fe3 plus. Oxide, an O ending. Oxygen's in group 6 with an oxidation state of -2. It means it forms 2 minus ions, gains 2 electrons to fill up its outer shell to get 8 electrons. So it's 3 plus and 2 minus. So if it's 3 plus and 2 minus, it must be 2 3 pluses and 3 2 minuses. It must be Fe2O3. So the 2 3 pluses balance out with the 3 O2 minuses. The next clue is that it's entropy of formation. So formation is to make 1 mole of it. So I've got to make 1 mole of this. It's a solid, and it's got to be formed from elements as you'd find them in the laboratory. So as you'd find them in their standard states. So entropy of formation to make 1 mole of this from elements in their standard state. So oxygen is a gas and iron is a solid, and to make 2 Fe2 I'm going to need 2 Fe's, and 3 O's is going to be 1.5 O2. That's your better answer. They will allow this one where you double it up, but that's your better answer because it makes 1 mole of Fe2O3, and that fits with the entropy of formation. Table 2 contains some standard entropy of formation data. Here's an equation. Use these data and the equation for the reaction of iron 3 oxide with carbon monoxide to calculate a value for the standard entropy of formation of carbon dioxide. So what you've got is you've got this reaction here. We know that's got an entropy value of -19, this reaction, because it tells us it here. I've got the entropy of formation of carbon monoxide. So carbon monoxide is formed from carbon and oxygen, as you'd find them in their normal states, in the laboratory. Carbon and oxygen to make carbon monoxide. Now, to make 1 mole of carbon monoxide here, it's -111. So to make 3 moles of carbon monoxide, it's 3 times -111, 3 times this value here to make 3 moles of carbon monoxide. To make Fe2O3, it's -822. So from elements in their standard states, so from some iron and some oxygen, then it's -822 for this reaction here. And therefore, to make iron from elements in their standard states, to make this Fe here, well, Fe is already Fe, so that's 0. And to make 3 moles of CO2, so I don't know that. That's what I want to try and find out. Find the standard entropy of formation of carbon dioxide. So I've got to find this value here, the entropy of formation of carbon dioxide from elements in their standard state. So all these elements in their standard states are either making or making products here or making reactants here. And I've got the values of each of them, -822, 3 times -1110, and 3 times something that I don't know that I've got to work out. So -19 from here to here equals this one from here to here, this one from here to here, and then coming round in this direction. So I've got to reverse the sign of 822, so that's +822. So -19 equals +822 to come round in this direction. 3 times -111 is -333, but I've got to reverse that sign because I want it coming round in this direction. So +333 plus 0 and plus 3 times the CO2 that I don't know. I can then take these to the other side. So -19 is -822 -333 -1174. So the CO2 divided by 3, and it comes out as -391.3, and it's in kilojoules per mole. Some enthalpy data are given in Table 3. Use the data from Table 3 to calculate the bond enthalpy of NH in ammonia. So let's take this equation here. The enthalpy value is -92 in this direction. So we must have some equations here. We've got N2 to 2N. N2 to 2N is +944. We've got 3 times 436 because we've got an H2 going to a 2H. So H2 going to 2H. 3H2 must be 3H2 going to 6H. So we've got this value here going to 6H. And I'll need to work out this value, NH3 to 2n plus 6h. So this is my missing piece here. So minus 92 is 944, it's going in the right direction, plus 3 times 436. And I want to work out what this value here is. It's going in the other direction, minus 2 times NH3, because that arrow needs to go in this direction. So these, the N2 and 3H2, coming down to these chemicals here, these atoms, and then going to two lots of NH3. If I reverse that sign, is minus 92. So let's take this across the other side. 2 NH3 is the same as 944 plus 1308 plus 92. 2 lots of NH3 is 2344. 1 NH3 is 2344 divided by 2, which is 1172. Now it actually wants to know the strength of an NH bond. So I've got the value to make NH3. And NH3 has got 3 NH bonds, so if I divide that by 3, if I take this 3 NH bonds in NH3, divide by 3, 390.7, but all these values here, I want to try and get to 3 significant figures, the same as these two values here, so 391. Give one reason why the bond enthalpy that you calculate in question 2.3 is different from the mean bond enthalpy quoted in the data book, because there are other chemicals with an NH in them. So the data book value is different from other compounds, is different in other compounds. So what that means is that there are other compounds with NH bonds in there. So it's an average. The data book value is an average of all compounds with NH bonds in there, and not just NH3 molecules.